As a part of reading course, we are going to start a presentation by Swapnil, who will be basically presenting the foundation of mathematics and logic. So it's my great pleasure to welcome Swapnil. Swapnil, please share your screen, and now the screen is yours.
Thank you, sir. One second. Is my screen visible?
Yes, it's visible now. Audible as
Okay.
well.
Hi, I'm Swapnil, and I'm going to be presenting today uh, th- some preliminaries and some basics of the subject of the foundation of mathematics, and I'll show how mathematical logic is used to study the foundations of mathematics. So today I'll try to answer or deal with these questions that uh, what is meant by foundations of mathematics and why is it important at all. Then what exactly is a proof? We have, or why is proof by contradiction a valid proof principle? Like in mathematics, we have been doing proofs and perhaps using proof by contradiction regularly without perhaps giving it a second thought. In this lecture, we'll try to do exactly that. And at the end, if there's time, I'll try to touch on this question that are there mathematical truths which
Okay.
math- mathematicians cannot prove even if they are given infinite time and resources. So let me begin my presentation. Uh, Remember, like in our second semester in our analysis course, we saw how reals can be constructed from rationals. Let me try to give a quick recap. Uh, from the rationals, if we take an equivalence relation on the set of rationals and say on sequences of rational numbers and say that two sequences two convergent sequences are equivalent an and bn if uh, if they are Cauchy. And then what we did was that each each equivalence class of these rational numbers actually represents a real number. And in this case of and then again we know that we can construct the rationals out of the integers. How do we do that? We again take a equivalence relation on the set of integers and say that two rationals a by b is equivalent to c by d if ad is equal to cb. Note that here uh, you know a multiplication is already defined in integers. So what we are doing is that we are defining rational numbers using the known properties of integers. Similarly, using subtraction, again, or if applying equivalence relationship on naturals, we can get integers. And similarly, from set theory, I'll touch on this point a bit. And from set theory, we can get naturals. How do we get? We say that in two sets, what we do is that we again use or define an equivalence relationship on the sets. And we say that two sets A and B are equivalent if there exists a bisection between A and B, which what I mean to say is that basically the sets A and B are of the same cardinality. Now each equivalence class in fact represents a natural number. For example, the number two might be represented by the equivalence class containing the sets, for example, uh, 1 comma 2, a comma b, or even goat comma cow. Like all this represents the natural number 2. Now, if we what are we doing here exactly? We are basically, we are developing mathematics or higher concepts of mathematics using more basic concepts. We are going back. So, very, a natural question arises is that what is there at the very beginning? What is here? Uh, what is it that is the holding up entire mathematics from which we can build up? So traditionally, we have heard that set theory is the foundation of mathematics, and but what do we exactly mean by that, or what is it like? What exactly is set theory, or uh, what are we trying to do? Like, let us try to look into these concepts more deeply, and we are going to. I will be going to give a non-technical uh, overview, and I will take you through the journey. Uh, I'll take you through the journey from the historical perspective, how or what happened and why it happened. Okay, so in Gottlob Frege, he was a German mathematician. He's perhaps the most important modern logician after Aristotle. And even during his time, logic was considered more of part of philosophy than mathematics per se, and the relationship between logic and mathematics was unclear. Mathematicians used logical reasoning, but logical reasoning was used everywhere, even in debates or whatever. There was nothing particularly special about logical reasoning used in mathematics, nothing new per se. It was rigorous, of course, but there's nothing new. So, but Gottlob Frege uh, started a program called Logicism, in which he he used to he started by defining mathematical concepts like natural numbers, zero, less than, these mathematical concepts using purely logical notions like like not, or, and there exists for all equality. And once he once defined, once basically mathematics was formalized, was written in the language of not, or, and these things, he used to derive theorems by purely logical rules of inference and from purely logical axioms. Now, what do we mean by logical rules of inference and logical axioms? Well, I'll come back to this. But his program was quite, although quite comprehensive, and actually failed. In fact, the story goes that after he had sent his book for publication, before it hit the markets, at the last moment, the British logician and mathematician and philosopher Bertrand Russell wrote a very devastating letter to Gottlob Frege that he has found a contradiction or inconsistency in his theory, or he found that using his theory, he could uh, that theory could prove that prove a statement of this form, that A and not A, like A is also true and not A is also true. So, and the contradiction, or this contradiction or inconsistency is famously known as uh, the Russell's paradox, where he showed that using Gottlob Frege's theory, he could prove the existence of a set X of where X is the set of all sets that does not contain themselves as their member, which means that okay, so like yeah, so mm, now the contradiction of this statement arises, like when we try to understand whether X is itself a member of X, or is it not? So I'm going to give you a brief idea how this is arrived at. Mm, So X is taken to be the set of all sets that does not contain themselves as members. Now, what happened was that, like in Gottlob-Frege's theory, it was permissible to a set to be defined if it is well defined. Now, so what we do is that let us let us divide all the sets into two categories. Let us call them ordinary and extraordinary. Now, they are ordinary if a set A is ordinary if A is not contained in itself otherwise, or A is contained in itself. Now it's clear that that any set will either be ordinary or extraordinary. These are mutually exhaustive and exclusive. And yeah, so now let us try to see whether X is ordinary or extraordinary, right? So say case one, X is ordinary. Now, if X is ordinary, right, then then because you see now look at the definition of X. X is a set of all sets that does not contain themselves as members, or in other words, X is the set of all ordinary sets, right? Now, if we assume that X is ordinary, then X will be element of X, right? Now, if X is element of X, that means X contains X, so X is extraordinary. Pardon my handwriting. And so you see there is a contradiction over here. If we start with ordinary, we arrive at extraordinary. Now if we say that X is extraordinary, then X, by definition of extraordinary, X is contained in X. But X is a set of all ordinary sets. Then how is it possible that X being extraordinary, it is the part of the set of all ordinary sets? Like, since X is element of X, we can say X is ordinary. So we see X can neither be ordinary nor be extraordinary, which is not possible. So we have arrived at an absurdity, a contradiction, so to say. So you see that, so this is what Russell's paradox tries to point out, that Gottlob-Frege's theory can produce inconsistencies such as these. Now, taking cue from Frege's program logicism, Bertrand Russell and Alfred Whitehead, wrote Principia Mathematica, in which again they tried to reduce all of mathematics to principles of logic and axioms of logic. And now they did it without any contradiction, but still, but the thing is that in their theory they took certain axioms which was which was not exactly logical and mathematical in some sense. for example, they use the concept of element of, uh, the thing we use, like A is element of X, the set, things like this. Element of is purely a mathematical notion and not a logical notion. Now, I will try to, in the course of the lecture, I'll try to give you more idea about what logical means. So this will become clearer why this is not uh, mathematical and not logical per se. So, although logicism as a program failed, it gave rise to a subject of study called mathematical logic. And uh, yeah, so like like seeing all these problems in the program of logicism, it was very unsettling because from the time of the Greeks, like uh, for example, Plato, in his at the entrance of his academy, wrote that uh, let no man ignorant of geometry enter. So Greek philosophers had a special place for mathematical knowledge. Why? Because they thought that mathematical knowledge is the one last reservatory of human knowledge, which is untainted by space and time, perfectly rigorous. So, but then when we are looking deeper, we are arriving at all these inconsistencies. So it was very unsettling for mathematics. And then also uh, the rise of non-Euclidean geometry. That so the story of non-Euclidean geometry goes as follows: that the fifth postulate of Euclid, which says that like the parallel postulate, that two parallel lines do not intersect. Like so, like if there is a parallel line and we have a point, we can draw exactly one parallel line through that through that point, which is parallel to the other line. So this postulate was like people like Lobachevsky, etc. Uh, they they showed the existence of non-Euclidean geometries, and like which was very unsettling. All the like because people always thought that the fifth postulate could be either proven using the other postulates of geometry, but here we got a geometry in which all the other axioms of geometry are hold true, but the last axiom, parallel postulate, is where it is false. So a lot of disturbance was going on. People, the last repository of human knowledge was being attacked. So David Hilbert gave the clarion call. So he started a program called Hilbert's program, in which he hoped that there would be a complete formalization of mathematics in axiomatic form, and he had mainly two focuses or two criteria. There were more, but these were the crux. That a proof of this axiomatization that mathematics is consistent in the sense that, for example, take the case of Euclid's five axioms. So what he wanted to say is that the five axioms held together will be consistent, and the proof of consistency he would use only finite methods. The proof will be finite. Now, what do you mean by consistency? And that is exactly what we are going to study next. What did he mean? So his slogan was to truth through proof. And what Hilbert wanted to do was he was happy enough because like we saw that how over here reals can be all boiled down to natural numbers. He was happy enough if he can prove the the consistency of of and completeness of natural numbers or number theory, or particularly piano axioms with which we construct number theory. So if we could prove the consistency of these axioms, then he was happy. But then something went wrong. We'll come to that later. Now let us take a deeper look into logic, the field of logic. and how it is related to the foundations of mathematics. So, so what is logic? Does anyone want to answer? Any idea what logic is? You can give an intuitive idea. Anyone? Anyone? Any clue? What do we do when we say logic? What is meant by logic? You can give your intuitive ideas. Anyone?
And it can be rational thinking.
Rational thinking, right? Anyone else? Anyone else would like to pitch in? Okay. So, in its most, I don't know, like a crude form, I'll show what I mean by logic by a picture. Over here we have certain facts. Over here we have some statements about facts. So what logic is, in generalized sense, how we go from this set to this set. This journey is logic in some sense. For example, in mathematics, when from one line of when you're doing a proof, you go to the next line, the thing in between is logic in some sense. And I think, yeah. So let me give you a brief introduction to one of the most, perhaps the most classical of all logics, and which has been done from antiquity since the time of Aristotle, but it has been formalized later, by through the works of Frege and Russell, etc. Now, what we will be doing here is mathematical logic. Now, the thing about mathematical logic is, like, if you notice here, this is purely a philosophical concept. So what we do in mathematical logic is that we use mathematical tools to reason about logic. It might seem a bit circular, but yeah, uh, but yeah. So, but this is what we do in mathematical logic, and the reason. Yeah. So, so let us start with propositional logic, where we'll get an idea of what we meant. Like, I'll be giving a very, non-technical tour of propositional logic, which is almost criminal, which is almost a criminal thing to do, because the study of logic requires only one thing: rigor. But the point of this lecture is just to give you an overview and a taste of what we do in logic, and how we use it to study the foundations of mathematics. So, propositional logic has some. Let's start with some axioms. It has three axioms: A implies B implies A, A implies B implies gamma, which alpha. It's kind of distributive. See, alpha implies beta, and it implies alpha implies gamma. And this is the contrapositive thing which we do. Not of alpha implies not of beta implies that beta implies alpha. Now, what are alpha, gamma, and beta? Those are formulae. Now, what do you mean? What do we mean by formulae? So if we 1 second. So what, like alpha, beta, gamma, etc. So I will define what we mean by formulae recursively. So start with some symbols, you know, P, Q, R, etc. Say perhaps the small letters of English language, and you can say that these are variables, or so these are atomic formulae, the building blocks. And now we say that if, and let us call the set of formula F, and let's define all of them to be element of F. Now if alpha is element of F, then not beta is also element of F. And now if alpha, beta element of F, then alpha implies beta element of F. Last is nothing else. So this is a kind of recursive definition. I don't know, yeah, recursive. So note that what this basically means is that, you know, we start with some atomic formula P, Q, R, S, T, and like what we do is, let's say P, because P, small p is element of F, it will imply that if, which basically says if P is a formula, then not P is also a formula, you know, and it says that if P and Q is a formula, then P implies Q is also a formula. Now you might think that, you know, like where did you know, and or not go? But in fact, you know, and or not can be defined using not and implication. How? Let's see. Alpha, sorry, alpha or beta is actually the same as uh, not alpha implies beta. So basically, you know, like think of or is, or as just a symbol, where, you know, what does this symbol mean? This symbol means this. You can look at it this way. Now of course, like we are more intuitively uh, you know, familiar with and or nor, we say that this is true if, you know, either one of them is true. And like similarly, and you know, alpha and beta can be represented as not. So we are, you know, if both of them are true, this is true. You see that this will hold. Now the main reason that, you know, we are using not and or sorry, not an implication to define these things is that because you know, we want our language to be minimal. There are reasons why we want it to be minimal. Uh, yeah, so I'll come back to that later. Why do we want it to be minimal? So just know that, you know, or and can just be thought of a symbol which means this, and you can, you know, you verify this thing using the truth table, etc. Yeah, so coming back, so now we know what a formula means, right? So all of these are axioms. These are just you know, like out of all the formulas, out of all, you know, if we take F is the set of all formulas, you know, we have taken out three formulas, three kinds of formulas actually, three formulas, you know, which we have given it a special name. From the universe of all formulas, if this represents all formulas, if we have chosen a very tiny, we call it axioms, and give it a special name. Now, why we are giving it a special name and why these, I'll come back to that later. So just know that we have taken it out and given it a special name. We have called them axioms. Right. Now, those were the logical rules. And now, remember Gottlob-Frege's logical rule of inference. One second. Logical rule of inference. So, what does this mean? So, modus ponens, or is a rule of inference. It basically says that from alpha, and alpha implies beta, we can get beta. Now, intuitively it goes something, intuitively it goes something like this, that if we know that alpha is true and alpha implies beta is true, then beta is also true, right? For example, giving you an example, and like why this is quite plausible, in fact, like kind of like human implies mammal, and if we know that someone is a human, we can conclude that he is a mammal. It's quite plausible, and in fact we do this all the time in mathematics. For example, giving you an example, in mathematics, for example, if GCD of a comma p is equal to 1, it implies that a to the power p minus 1 is congruent to 1 mod p for Distributive theorem. And if we already know that the GCD of a comma p is 1, we can conclude that a to the power p minus 1 is congruent to 1 mod p. So like we are using this rule of inference always in mathematics. Okay, so like, does anyone have any question about this? Because I know this might be a little bit confusing. Any questions?
No, Swapnil, please continue.
Okay. So this was just the intuitive idea of why this is correct. But now think of it formally. Like over here, we are not talking about any meaning. We are just saying that if there are two strings, when I'll regularly study proof, this will become more clearer. When there is alpha and alpha implies beta, we can get beta. Yeah. So now I think we have enough tools in our hands to answer the question, what exactly is the proof? Okay. So we say that alpha is derivable or provable from x. This is the simple alpha x turnstile. This is called turnstile alpha. This is a classical notation used in logic. uh, or it kind of means that alpha is provable from X. Basically, you can think of it as like this. For example, these are the assumptions, like like always related to your practices in mathematics. So if you do that, then you will be able to grasp what this dry formal symbols actually mean. So this means that if we take X, if we take a set of assumptions X, then we can get alpha. Like from the set of assumptions X, alpha is provable. So this is what it means. Now, what is a proof? When do we say that X turnstile alpha? Yeah, we say alpha is provable from X when this is important, when there exists a finite sequence of formulae alpha 1, alpha 2, alpha n such that there are certain conditions. First condition, alpha n is actually alpha. Number 2, alpha I, oh, sorry, no, this is number 2. Alpha I element of X or alpha I element of axioms. Like what I'm just doing over here is that taking these 3 axioms and saying constructing a set which we are calling axioms. Using, like, basically we are taking a set and we are putting these 3 formulas inside the set. So that's what we mean by set of axioms. So what it means that either xi is a part of the assumption, or this is called premise in logic. Premise, and this is conclusion. Set of premise or assumption, or xi is either axiom or xi is obtained from earlier elements of the sequence using the rule of inference modus ponens, MP. It is abbreviated as MP, modus ponens. So what it says that this sequence of formulae, in this sequence of formulae, either each xi is either first of all, of course, xn has to be alpha n has to be alpha, and alpha I either has to be a part of X, or has to be an axiom, or can be obtained from earlier elements of the sequence using modus ponens. Let me give an example to show what we mean. Let me give an example of a proof, a formal proof, to explain what we mean by a proof. So yeah, and there is just one thing I want to say. If the premise set is empty, so if the premise set is X is empty, and so we write something like this, either we can write the empty set in turnstile alpha or this alpha. So when the empty set is empty, so when the premise set is empty, we said that alpha is a theorem. It does not require additional assumptions to prove it. Okay, so let us try to prove that this thing alpha implies alpha is a theorem. Like just always connect it with mathematics. So it's like 2 is even implies 2 is even. It is always kind of true. I'm using the words true, but I have not defined what true means. But just to give an intuitive feeling of what is going on over here. Okay. Uh, so let us try to prove this. Alpha implies alpha. Very formally. 1. We are trying to create a sequence of, yeah. So 1 represents the first, like alpha 1, something like that. So alpha. Anyone? What is this? This is one of the axioms. Can anyone guess which axiom? Which axiom are we talking about? So we are talking about the first axiom. Alpha implies beta implies alpha. See, so where this is beta, so this is axiom 1. Number 2, it will get complicated and pretty and ugly. Sorry for the inconvenience. Yeah, number 2. Yeah. Notice that this is the second axiom. Okay, let me write the axioms over here for reference. How should I do it? I don't know. Okay, so this is basically this distributive axiom which says that, oh yeah, this is better. I can do it like this. Alpha implies beta implies gamma. This implies that alpha implies beta implies. So notice that the form of this and this is the same. This is basically, we are using the second axiom. In place of beta, we are using, alpha implies alpha. In place of gamma, we are using alpha and alpha for alpha. So, like we're distributing it. So this is of the same form. and the first one we did, alpha implies, this is the first axiom, right? Notice the same, this is the same form where beta is, represent over here, it is substituted kind of by alpha implies alpha. Okay, now let us proceed in the proof. Now see, what we do is that, notice that this part, this part and this part is the same. So what can we do? We can apply modus ponens MP to get this. Now again, we can notice that yeah. So now again notice that this is actually the first axiom. So we apply, we again apply modus ponens and we get alpha implies alpha. Axiom 1, comma, this statement 3, and the modus. So what we arrived at alpha implies alpha. This is what we wanted to prove. So now, like, I'll show you like how we construct a sequence. Like, for example, let's say alpha 1, alpha 2, alpha 3, and alpha 4. This is nothing but. So alpha 1 is basically this string of symbols. Alpha implies, alpha implies alpha. So an alpha 2 is this, and alpha 3 is this, and alpha 4 is this. So notice that this, this sequence of formulae, which finishes with what you wanted to prove, is actually a proof. Why? Notice. Now, the first criteria of what a proof should be is valid. Okay, because alpha n is this what you wanted to prove, the alpha 4. Now alpha 1 is axiom, so okay, it can be each xi is either an axiom or an element of premise set. The premise set is empty, so we don't have to worry about that. Axiom or obtained from earlier elements of the sequence using modus ponens, right? Okay, so alpha 2 is the second axiom, right? So it's all right. Now alpha 3, notice over here, alpha 3 is obtained from alpha 1 and alpha 2 using modus ponens. So this is also a correct element. And now again alpha 4 is obtained from axiom 1 and 3. So again using modus ponens. So again, this is a valid sequence of formula which finishes with what you wanted to prove, and hence this is a proof. Now this might seem little bit tedious and rather dry thing to do, but there's an important thing which I want to point to you guys. That notice that what we are doing here is just a manipulation of the string of symbols. Important thing about this is what we call a formal proof. Important or useful thing about this is that this can be read and done by a computer even. It is completely mechanical, so as to say. There is nothing creative or which we generally do in mathematics. So one step directly follows from the earlier steps. So that is the reason why this kind of proofs are important for computing. But we are not bothered in this lecture. We are not bothered about its implications in computer science. What we want to understand is its implications in the foundation of mathematics. Now notice that the proofs that we have been doing in mathematics, in some sense, this is a generalization of what we have been doing. Whenever we do a proof in mathematics, during doing the proof, a statement is dependent on the earlier statements, isn't it? Like we start with something, we know we have to prove something, say, given that we have to prove something. We start with something we know, and from this we come here, we add new axiom, we add new statements that we already know, and finally at the end of the proof, what do we have? What we wanted to prove. And so this is a correct derivation. So you can think of your proof, whatever proof you do in mathematics, as a sequence of steps. This is the concept that we have tried to generalize in logic. And so thing is that in logic, what we do is that these, we try to rigorously capture these notions of what we are doing exactly, precisely, like mathematically precisely, when we are doing mathematics. Yeah, so this is what is a proof. So this is one of the things I promised to answer. So in some sense, this is what is meant by a proof. Okay. Does anyone have any questions or doubts? Okay. Okay, yeah. Notice one thing. Notice one thing, that over here we never mentioned anything about meaning or something else. What we just wanted to do, like this was just a symbolic manipulation of the symbols. Now let us try that. What there are in every logic, there are two aspects: semantics and syntax. Semantics means giving meaning, like dealing about issues like truth, etc. And syntactics mean, manipulation with symbols, which even a computer can do, mechanical. So now what we do is that, we define a, let's see how can we give meaning to it. Let's just take a function which we call valuation from the atomic formulas to 0 and 1. Like for example, p q, either, p is mapped to 1, say, or p is mapped to 0, anything, q is mapped to 0. So where p, q are the atomic variables, the starting points of formula. And now we define a valuation from all formulas to 0, 1, where v of not alpha is equal to 1 if, like, we define it recursively. If v of alpha is equal to 1, and we define equal to 0 if so notice that what we are trying to do is that we are trying to again recursively define the function v using so at the, like, using, so basically look at this. I'm giving you an intuitive idea. So alpha, the valuation of not of alpha is dependent on the valuation of alpha. It's quite evident. Not of alpha is 1 if the valuation of alpha is 0. And like we are doing it inductively, right? We are starting from atomic formulas and building it up. And yeah, like alpha implies beta is true if this is, yeah, valuation of alpha is 1 and the valuation of beta is 0, and it's otherwise it's always 1. Yeah. So now let us talk about logical consequence. Now we did what we did proofs and deductive. So there is another aspect to it, which we call, when we look at, like, this is kind of the semantic side, or the meaning side of what proof or derivability is. So we say that alpha is a logical consequence of x if for all valuations, by valuations we mean that so basically if we give, we can give any valuation, whatever we choose, to the atomic formulas, but then all the other formulas, all the complex formulas like alpha implies beta, not alpha, are dependent on the valuation we give to atomic formulas, right? For example, yeah, so like for example, if v of alpha is 1, then v of not of alpha is 0. It is fixed. This is fixed. We are just free to give valuation to the atomic formulas. Okay. For all valuations v such that all formula alpha, such that for all formula alpha, p of alpha is, all formula beta, v of beta is true then if V of alpha is true, which means that if all the statements in this set is true, then alpha is true. If that is the case, if for all valuations, whatever valuation we give to the atomic formulas, if all the formulas in alpha are true, then all the formulas in X are true, then alpha is true. Now, what I mean by true, I mean, if V of alpha is given 1, then we say true. V of, alpha or beta is given 0, false, then we say it's false. Okay. So notice that this definition has nothing to do with the definition of probability of proofs that we gave over here. Like, we wanted a finite sequence of formulas such that this happens, right? But yeah, so this has nothing to do with this, right? Like, at least one might not guess. Now, for example, let me give an example of what I mean by this, like semantic valuation function. For example, look at this. What I mean is that, for example, let us take this formula. Alpha implies beta implies alpha. Now I'll be doing a truth table. I hope everyone is familiar over here. So notice that this formula is dependent on its atomic formula. So whatever value we give, for example, 0, 0, 1, 1, 0, 1, 0, 1. So, sorry, if this is false, right? If whenever the antecedent of an implication is false, then obviously it is true. Alpha is 0, then this will always be true, because you remember how we gave the valuation of alpha implies beta. We say that it is only false when this is true and this is false. So in either of these cases, this is false, so it's true. So now in this case, now alpha is 1, now beta is 0. Now again, if beta is 0 and alpha is 1, we know that this is true. So entirety of this is 1 and this is 1. The entirety of this will be 1. And again, like, if this is 1, sorry, beta is 1, alpha is 1, this is 1, this is 1. So yeah, so so notice how once we give valuation to alpha and beta, we know the valuation of this. And in fact, note that this is a tautology. What do you mean tautology? Tautology is a formula, string of formula, which whatever valuation we give to the atomic formulas does not matter. It will always turn out to be true. Now, I know you might be thinking, I chose a special formula where this was axiom, but this is what I wanted to point to you out. Now, this is the connection. Now, this is the reason why we chose the specific axioms. We chose the specific axioms because, firstly, all axioms we chose, if we, over here, if you try to do the truth table of these axioms, all of them will turn out to be tautologies, which means that no matter what valuation you give to alpha, beta, gamma, this thing, the value of this entire formula will always be true. So this is the reason why we chose that particular tautology. So axioms are always now and then contradiction, like if you just take the negation of this will always be 0. So this is a contradiction. So this is an example of so like, for example, this statement, this string of symbols, formula is always true, whereas this string of symbols is always false. We call this a contradiction and this a tautology. Now, the main thing I want to point out, or the interesting thing, is that you see the way we define logical consequence has, on the first look, has no connection with how we define proof, right? Over here we are talking about valuation whenever all the formulas over here is true, this is true, but whereas when we talked about proofs, we wanted a sequence. But the interesting thing is, which you can prove using mathematics, in logic, is that it is sound, which means that if alpha is provable from X, then alpha is also a logical consequence of X. And also, if alpha is a logical consequence of X, then alpha is provable from X. So indeed, so in fact, this can be proven. So this is rather shocking, I think. But this is like, because of this specific reason, in mathematics, whenever we are not very much bothered about truth and proving, because if it's proven, it's true. This is what Hilbert meant when he said through truth, to truth through proof. In math, to truth, because of this reason, because of this specific reason, in mathematics, we can so casually use proving to arrive at truths. We are not so bothered about the difference or distinction between syntax and semantics, proofs and truth, and things like that. Why? It is because of the safety or the security of this soundness and completeness which mathematical logic has provided us. Because of these, we can be, when we are doing mathematics, we can be ignorant of the subtleties of logic, because of it is taken care of. And then I think I'm going to end, because I don't have much time. I'm going to end by why we use proof by, or what guarantees, or how can we use proof by contradiction. Give you a taste why. Now, I'll not be proving all these. So in logic, these can all be proven. And after the lecture, I'll give you a reference from where you can learn all these, or you can even ask me. But yeah, so the deduction theorem states that if alpha is derivable from beta, if beta is derivable from alpha, then alpha implies beta is a theorem, and vice versa. Notice that we use this in mathematics always, don't we? We start with an assumption, some alpha, and then prove beta, and we conclude that alpha implies beta. Now, why can we do this so casually in mathematics? Because of the deduction theorem. Again, the deduction theorem, provides the security, or this thing we can use. Again, so again, the subtlety of logic can be ignored by mathematicians because it is taken care of. Yeah. And now, so this can be generalized. Sorry, I'll write the generalization. It says that if tau is a set of formula, then beta, if and only if, over here tau was basically the null set. It says that tau union of alpha turnstile beta, then tau turnstile alpha implies beta. Now I'm going to talk about a thing as system explosion, and yeah, I'm going to end with this. So so this is in fact a theorem, not of alpha implies beta. I'm not going to go over the proof because of lack of time. So you can check it over here. Again, we start with axioms. You see a sequence of steps, and in which the last element of the sequence is basically this. We use axioms and MP. So what is important is that this is a theorem, not of alpha implies beta. So now we know not of alpha implies alpha implies beta. Now by converse of dt, note, I'll write it over here again. Okay, see, if and only if, so we apply the converse, we take it this side. Not of alpha turnstile alpha implies beta. Again we take it this side. Not of alpha comma alpha implies beta. Now what this means is that basically if in our premise set we have something of something of the sort that alpha and not of alpha, then any formula can be implied. This property is known as explosiveness, and this is the specific reason why we use proof by contradiction and why we are so worried about consistency. We say, okay, I'll come to it. We say that the set tau is consistent if it does not exist any alpha such that tau turnstile alpha and tau turnstile. So what happens is that if this happens, right? Like remember the Russell paradox. If this is the set theory or logical axioms implies that x is ordinary and tau implies x is extraordinary. What will happen in this case is that what happens is that because this is a theorem, and we know that tau implies alpha, not of alpha, from here, we applying modus ponens from these two, we get what? We get tau turnstile alpha implies beta. And again, because tau implies beta, again we apply modus ponens over here to get tau implies beta. And beta can be anything. So what it basically means that if a set of formula gives the inconsistency means that the definition of inconsistency is that if alpha is said to be tau is said to be inconsistent if it proves alpha and also its negation. There is alpha such that. So the thing is, what it kind of means is that, for example, if in group, let's take the example of group theory. If the axioms of group theory, like associativity, existence of inverse, or identity, if these are inconsistent, what would happen is that whatever statement you can write in group theory will be true. So basically, in that theory, whatever statement you write using whatever statement you write, they will turn out to be true. And it's meaningless and it's not interesting. If everything is true, then what's the point, right? For example, so it will be something absurd, like what I mean to say is that, for example, if we have a contradiction in number theory, say if 2 less than 4 and 4 is less than 2, if we have these two statements, we can in fact prove anything of the sort, anything that 2 to the power 100 is equal to 2, anything we can prove. Like just given these two, we can prove anything we want is equal to 5. So the theorem becomes boring, and the system explodes, so as to say. So this is the reason why we use, or why we can use proof by contradiction, because once if the set is inconsistent, then we know that something is wrong, right? So I think I have to stop here, but let me just sir, can I have 5 minutes more?
Yes, you have.
Okay.
Please.
So I'll say I'll give you an idea. So what we did, we got a brief overlook of propositional logic, just to give you a taste of what we do in logic. But in fact, the logic used in mathematical reasoning is first order logic, in which there are other symbols and axioms involving for all and there exists, because for all and there exists are always required in mathematics. So now let us go back and see what Frege's logicism meant and what we do basically in mathematics. what we basically do is that, remember the three axioms we had in propositional logic, axiom say 1, axiom 2, axiom 3. So for example, in what we do in number theory, and we had what MP. So what we do in mathematics is that using these three axiom modus ponens together with the Peano axioms, like I'm talking about number theory. For example, Peano axioms like associativity x plus y plus z is equal to, or whatever. Like in induction, I'm not rigorously saying, but you remember, right, that all those axioms of Peano arithmetic could be written in, rigorous, formal language. So together with this and Peano arithmetic, what we get a theory. What do we call it? We call it number theory. Number theory, what we do, we study or try to find out all the theorems from all these, whatever we can get. So, like we have been always using these, but at the back, we have always been using these axioms. So, but if we have to study the foundations, we have to delve deeper into these things. This is, what logic and the foundation of mathematics does. Or in, for example, group theory is nothing but the group axioms. Instead of Peano arithmetic, you take the group axioms like associativity and existence of inverse and identity. That, for example, for all x, there exists y such that for all x, I'm writing it quite informally, for all x, y dot x is equal to x, and x dot y is equal to x. So where y is basically the identity. So, like for example, in this way, we can write the axioms or whatever formally of group theory also. So basically, this is what we do in mathematics, and this is what Frege wanted to do. What he wanted to do was that start with certain axioms, and with the axioms we require. Basically, you can think of these as assumptions. When we did proof implies alpha. See, these are always there, axioms. But in the assumption set, we just take the Peano axioms or the group theory axioms or whatever. This is what we do in mathematics. But these are all, yeah. So, and I'm going to end by just talking about giving what Gödel's incompleteness theorem is. Quite famous, and some say that this was the birth of modern logic. And in the sense that this was the theorem which moved the study of logic from philosophy departments to mathematics departments, and it almost started the subject of mathematical logic. The theorem says that the theorem says that if the Peano axioms are consistent, then it's incomplete. Now we know what inconsistency means. That if P represents the Peano axioms, that if consistent, which means that that there does not exist alpha such that and not of alpha. It's quite now you understand why consistency is quite reasonable, and why Hilbert's program, Frege, etc. was so bothered about consistency. So it's quite reasonable, right? If it's not consistent, then anything can be implied, right? So what Gödel's incompleteness theorem says is that, for example, in the case of Peano axioms, is that if like in the case of number theory, if the number theory axioms are consistent, then it's incomplete, which means that there exists an alpha such that alpha may be true, but alpha is neither provable nor alpha nor not of alpha is provable from P. Notice you might think that I said that x turnstile alpha if and only if x double turnstile alpha, but note that was only for the axiom. This I said only when we said only for propositional logic or first order logic or whatever. Like whenever we bring in extra axioms to try to do mathematics, that thing changes. This is not always true. It's not always the case. So this is not always so like this is a common point of confusion. So yeah. So yeah. So what it says is that that if alpha like we will get a formula alpha which is true, but we'll never be able to prove it in the system of kind arithmetic. So I come back to what the three questions I initially wanted to answer. What is meant by foundations and why it is important. I hope I gave uh, a taste of what we do in foundations. Questions like what is a proof, we have a better idea now, and why proof by contradiction is a valid proof principle. And finally, like there are mathematical truths that mathematicians cannot prove even if given infinite time and resources. It's quite unsettling. And this was the death knell of Hilbert's program, actually. But that's another story for another day. But it gave rise to a subject called mathematical logic, and it has wide applications in theoretical computer science. In fact, it has found more application in theoretical computer science than mathematics. Mathematics, analytic philosophy, linguistics, a whole lot of areas. So that was my presentation. Thank you all. And like now, if anyone has any question.
Swapnil,
Yes, yes.
so the theory of mathematical logic, as it seems that if we can feed these informations or the main basic axioms on a computer, then can it prove or disprove any mathematical statement which are really complex for a one person to do it rigorously?
Yes. So therein comes the So there are two things: checking and proving. Given a proof, checking a proof is not difficult. You see, right? Because like there are fixed rules, so it will not be difficult. Now the
No,
question of
there may be some inconsistencies in the arguments presented by the person who have proved it. So you have to spot those inconsistencies.
yeah, that can be done, right? That can be done. But there's one thing. So, but the thing is, for example, just giving you now, then comes in the concept of decidability. Now, what are the recursively, innumerable theorems, eh, which vaguely means that what all theorems can uh, the computer prove. In fact, the interesting thing is certain things like propositional logic is decidable. A computer will be able to prove all the theorems in propositional logic. It is decidable. But for example, first order logic, the logic we use in mathematics, is not decidable. And to give you some ideas of some decidable things, abelian groups, the theory of abelian groups, if we take the group theory axioms together with the commutativity x plus y is equal to y plus x for all xy, in fact, a computer can prove all theorems or can derive all theorems of abelian groups, but not of all group theory. So, yeah. So, the theories of, but like number theory, set theory, these are all undecidable. Computer, will not be able to list all the theorems, so as to say.
So that means there is not a complete set of axioms by which we can prove everything, right?
So that is the search for foundations of mathematics. That is the holy grail of foundations of mathematics. So like to find but those are actually different questions. What do you say? Like one thing is about computers trying to prove theorems, and the second is finding the concrete foundations with which we can do mathematics. So like the search is still on. Like category theory is a rival of set theory, so as to say, in doing certain things. Like I know of whom, like, yeah. So yeah. So does that answer your question?
Yes.
Anyone else? All right then. Oh.
Okay, so
Hmm.
Sarah is a bit busy now, so Sarah's asked me to end the talk, and I'd like to thank Swapnil on behalf of all of us. It was a very nice talk and very interesting one, because we have been doing mathematics through the last 2-3 years and maybe before, but it is very eye opener for us to find out that the belief that we have from childhood that everything in mathematics is provable is not true, or not so fast to prove. It requires a lot of logical reasoning itself, or mathematical reasoning itself, to prove that mathematics is provable. So it is very interesting, and a very interesting talk from Swapnil. So thank you.